It's been done. So we're very happy to have today Shalabh Bhatnagar from the Indian Institute of Science, Bangalore. He's a very well-known expert in various types of various problems of stochastic approximation, stochastic gradient descent that he's going to talk about, and so the talk today will be about doing stochastic gradient descent with only function evaluations, Fourier function evaluations with reduced bias. So with that.
Yeah, thank you. Thank you very much. Maybe I'll stop my video just to save on bandwidth. Am I audible?
Yes.
Okay, thank you. So this what I'm going to talk about is essentially joint work with L.A. Prashant, one of my former students who is now at IIT Madras. And he is a student of his by name Somen Pachal. So there's a lot of work that Somen has done, and essentially, so I'll talk about largely this work that we have done recently. And so the outline is essentially going to be the following. I'm going to briefly introduce what essentially is optimization under noise, and what do we mean by that in a sense. And it turns out that when we talk of optimization when the parameter dimension is significantly high, and then random search techniques are essentially those that optimize on the amount of computational effort to a large extent. So I'll talk briefly about random search techniques that are available currently, and then our contribution in this work to the class of sort of random search techniques, where we kind of generalize what is already available in the literature. And then I'll talk briefly about some convergence aspects of how one can analyze convergence of such schemes using a differential inclusion kind of a perspective. And then some simulation results that Somin had gone over. So largely this talk is going to be based on this work. It's currently under submission to a journal. And then as far as the convergence analysis is concerned, I'll appeal to some of the results that have already appeared. Okay, so the basic problem is the following. So let's say that you have a function j that is a mapping from r power n to r. And this is a given, this is some objective function. But this objective function has the following form, that j of x, give me a parameter x, and j of x is the expectation over noisy cost samples of h of x comma mu. Now, mu here denotes noise, and the E mu is the expectation under the distribution of that noise. Let's assume for a moment that this noise is IID. And so j of x is the expected value of this for any given parameter x. So to visualize, let's say on the x-axis you have the parameter, let's say it's a scalar. And on the y-axis you have a function j, which is also a scalar valued. So j cannot be plotted directly. All you have is, let's say, for different sample paths, you can plot out different trajectories that this would take. So let's say hx mu1 is this, hx mu2 is something else, and so on. Now hold on to any x and then draw a line parallel to the y-axis, and then look at all the points that fall on the dotted lines. Take their averages and call that as the j of x at that particular point. So the solid line here essentially corresponds to the function that is being averaged over all of these dotted lines. Now, the thing is, well, if you were to find essentially the objective, of course, is to find the minimum of this j of x, find a parameter x that minimizes j of x, which essentially boils down to saying this. But the point is that, well, we don't know what j of x is. I mean, all we can observe is these noisy estimates of the function h of x comma mu for different values of x. I mean, you can have these noisy estimates coming in. The question is, well, there are two ways of looking at it. One way is what I just described. I mean, you try to plot out this whole function, j of x as a function of x, and then try to say, well, now it looks like, well, the minimum is somewhere here, because I know what this function is, how it looks like now. But do we really care about this? Do we really care about finding the whole of this function and then looking for the minimum? So stochastic approximation kind of approaches help in this regard. So what they do is you really don't need to figure out what the entire form of that function is. So it's this area as such started out by a paper by Robbins and Munro. This was in 1951. And the problem they attacked was the following. So what they said was that let's say we wish to, solve a system of equations of this type, where J is some mapping R power n to R, where theta is an n-dimensional parameter. And the problem is, of course, we don't know the functional form of J. And what we do know is you have some noisy measurements. Let's say you have measurements of this type coming in, J theta n plus noise, where this noise is like a martingale difference sequence. In fact, in the earlier slide, I had noise which appeared as an argument of the function, and then you are taking the expectation over it, and you can actually show that this kind of a noise, which is an additive noise, can be written in that form as well. So basically, that form can be reduced down into this. So this is a fairly general way of describing it. It's just that this is no longer IID, but a martingale difference. So the idea then is that suppose you think of it this as a box. If you input in theta a parameter, what you observe is not J of theta, but J of theta plus noise. Okay, the noise corrupted observation of J is what you are observing for any given theta. So what Robbins and Munro said was, well, the objective now is to find a theta that solves this equation, J of theta equals 0. They suggested this algorithm. What they said is, as long as you allow me any number of measurements, so for as many parameters as I wish to. So suppose theta n is the parameter at the nth update of this algorithm. So you plug in theta n, you don't observe J of theta n, but you observe J of theta n plus noise. So you observe this is a noisy observation. You multiply it with some step size, or what we refer to many times as the learning rate in machine learning parlance. And then you add it to the previous value of theta that you have to get a new theta, and you keep repeating this. The interesting thing is that under some conditions, one can show that as n goes to infinity, theta n will converge to some theta star, and that theta star is such that J of theta star is actually 0. So again, recall the objective was to find a theta star for which J theta star is 0. You don't know the analytical form of J, and this approach allows us to actually get there by just using these noisy observations and without really trying to estimate what that J theta is across all theta. Okay, so if you've done this algorithm, it will eventually just converge to a theta star for which J of theta star is 0. I mean, that's the interesting thing about this algorithm. Now, convergence of these algorithms over a number of years, there has been quite a significant refinement to the analysis that is available. So initially, of course, it started out with this paper of Robbins and Munro. They assumed IID, additive noise, and then they showed that the algorithm is convergent in a mean squared sense. But over a number of years, I mean, so people have come up with conditions that are less stringent and essentially, okay, so they have also come up with derived conditions where you have martingale difference noise, you have Markovian noise, and so on. And you can still get to the 0 of such a function. Under so as I said, under less stringent conditions, and you can also get almost sure convergence. As applications, one can think of, let's say, noisy fixed point computation. So the idea could be, well, you want to find a theta star for which f of theta star is theta star itself. And in such a case, and you have only noisy measurements of this function f that are available to you. So because we are aiming to find the 0 of a j of this function j, you can form j of theta as f theta minus theta, and of course you add noise and so on. So you have these noise corrupted measurements of j. And once it converges, you know it's the point theta star for which J theta star is 0, and thereby F theta star equals theta star, which means you have converged to a fixed point of this function F, which is not known to you, right? I mean, so all you have is noisy observations of this function F. The other possibility is you have a noisy gradient scheme like the one I just showed, where the objective is to, let's say, find a local minimum of f. So in such a case, you can set j theta to be minus grad f of theta, and then you have noisy observations of grad f. And then upon convergence, you observe that you converge actually to a local minimum. In fact, one needs to argue, it requires some argument, but that it actually converges to a local minimum, but you can show that. So here is a general convergence result. Uh, so what it says is that suppose J in general is a function from Rn to Rn and its Lipschitz continuous. The learning rate satisfies these two conditions. In general, of course, you need it to be positive. An should be positive for all n. But in addition, sum over n, an is infinity, sum over n, an square is finite. So the easiest way to look at it is suppose an is 1 over n. Or maybe an is 1 over n power alpha, where alpha is more than 0.5 and less than or equal to 1. So those kind of an's sequences would work typically. Mn in general is a martingale difference with respect to a filtration, and this filtration can be at time n, it is the sigma field generated by theta m and all these mm's, m sub m's for m less than or equal to n. And in addition, what you also require is that the expected value of norm mn plus 1 square given fn is upper bounded by some constant k into 1 plus norm theta n square. Now, this is not, yeah, I mean, this is some condition, but it's seen to be satisfied by many applications, particularly when it comes to reinforcement learning algorithms and so on. You can actually verify that this is not such a bad condition. I mean, martingale difference is okay, but then this is also not too bad. But the more important requirement is this, that the supremum over n of norm theta n is finite almost surely. What it says is that your iterates are not going to diverge on any sample path. So on any sample path, you can always find some bound such that the iterates will stay within that bound. Of course, that bound will vary with the sample path. I mean, that much is for sure. But then it doesn't blow up. I mean, so you need to make sure that this is the case. Many times, so in analysis, people assume directly that this is what it is. But yeah, we have done a lot of work where we actually derive conditions under which one can prove that this is the case. But once this is so, then you can actually argue that under these conditions, theta n sequence will converge to some set A, almost surely, which in general is a sample path dependent compact connected internally chain recurrent set of this ODE. Now, compact connected, I am sure all of you know, if you don't know what is internally chain recurrent set, I mean, don't worry too much. But just as special cases, you can have attractors and so on, attractors of the OD. So it will, so if you have attractors, if you only have attractors, then all you can say is that, well, if your algorithm comes within some neighborhood of the attractor infinitely often, then it is going to converge to that particular attractor. I mean, those kind of results you can actually prove. So this is more general. This says that, well, suppose your limiting set is not even an attractor. I mean, so it could be some periodic orbit or it could be something else. But as long as you can ensure that so as long as you can ensure that it's compact connected and this uh, technical thing called internally chain recurrent set of this ODE, you can ensure that the algorithm will be convergent at least to such a set. And this kind of an analysis in the most general sense was due to Benem in this paper of 1996, and then this is also available in Borka's book on stochastic approximation. Okay, let's get back to our simulation optimization setting, where we are trying to estimate the gradient of the objective function, which is an expectation over these noisy cost samples. So suppose we are in a situation where if you take the gradient of this j of theta, which is gradient of E mu of h of theta mu, suppose you are able to interchange the gradient and the expectation. Now, in general, you cannot do that unless you have some smoothness conditions on the sample path and some extra regularity and so on. But so let's assume let's say the mu is over some finite set. I mean, then you have this summation over. I mean, so this summation is a finite sum, so you can take the gradient, push the gradient inside. But in general, if it's like an infinite sum or it's an uncountable set over which you have this measure mu, then essentially you need some justification for pushing this inside. But suppose those conditions are met for a moment, and you can actually push this gradient inside the expectation. So in such a case, of course, the gradient of E mu will be E mu of the gradient. And if you were to look at then the resulting scheme would then be you update theta in this manner, that the new theta is the old theta minus an, and then you have these sample gradients that you can find. And if you run this, then what you can do is to take the expectation. See, the nice thing about stochastic approximation is that the expectation can be obtained almost for free. You can sort of push in the expectation. So you can all you can do is to say that this can be rewritten as minus an into the expected value of this, and then plus noise term. Now the noise term being the gradient minus the expectation, and which is a zero mean martingale difference, a sequence by itself. And you can argue that ultimately that martingale, the resulting martingale that is there will be almost surely convergent. And therefore, it makes sense to sort of look at this expectation of the gradient here, but then the expectation of the gradient is the gradient of the expectation. And so you can see that then it is gradient of j of theta, and which is now a gradient descent algorithm, the usual gradient descent, which will converge to a local minimum. Such schemes have been well studied in the literature over a number of years. These went under the names of infinitesimal perturbation analysis or likelihood ratio kind of approaches. So this is a good reference of Yu-Chi Ho and Shiren Chow on perturbation analysis of discrete event dynamic systems, which sort of caters to many of these approaches that are already there in the literature. In situations where that aforementioned interchange between the expectation and the gradient operator is not allowed, you cannot justify it, then what you can do is then what one needs to do is to look at what we refer to as zeroth order methods. So the first such zeroth order method was due to Kiefer and Wolfowitz. This appeared again in the Annals of Mathematical Statistics in 1952, 1 year after the Robbins-Monroe algorithm came. They actually make use of the Robbins and Monroe algorithm, but they have a way in which they estimate the gradient. So what they say is that, well, you run 2n simulations, one with, because n again, remember, is the parameter dimension. So what they say is you run 2n simulations, one with this parameter, theta 1 plus delta, and then theta 2 to theta n. The second simulation with this parameter, where this plus delta has been moved from theta 1 to theta 2 now, and this goes on all the way to theta n, the nth parameter, parameter component. So these are the first 10 simulations. First 10 simulations, first simulation with this parameter, second with this, and so on up to the n. And then the n plus first is run with this parameter. So instead of plus delta, you have minus delta, and then plus 2, the 2th simulation is run with this all the way up to 2n. Okay. The way they formulate the gradient estimate is in this manner. You look at the noisy cost sample that you obtain with theta plus delta EI, as your EI being a unit vector with 1 in the ith place and 0 elsewhere. And all of these are IID, as assuming mu1i, mu2i are IID. So you form your gradient estimate by taking the difference between these two, the performance of the sample performance obtained from the first simulation and the sample performance obtained from the second one, divided by 2 delta. And then you run this usual stochastic approximation recursion, but with this FDSA estimate plugged in. And then you can argue that, this will converge to the, again, a gradient. This will converge, of course, in the limit as delta goes to 0 to, let's say, a local minimum. The problem with this scheme is that it requires 2n parallel simulations, as you notice, for one parameter update. Now, when n is particularly large, this is not going to be a very efficient algorithm. Simply because you require so many, particular, so many simulations to go over. And if, for instance, if your n is like 10,000, then you need 20,000 simulations just for one parameter update, which is not something that is a very useful technique. Then there was this paper by James Pal, and of course, in between there were other papers. What they said was that, well, we'll cut down on the number of simulations by using random search approaches. So what Spal does is that, well, in this paper, is that he runs just 2 simulations, and these simulations are run with these 2 parameters. Now here you see some extra delta 1, delta 2 up to delta n coming in. So these are like IID Bernoulli random variables. They are all plus minus 1 with probability half. Okay, so you just toss a coin each time. So you toss a coin n times. Plus 1 if head shows up, minus 1 if tail shows up, and then you perturb the parameters in this parameter in this way by taking plus delta delta 1 plus delta delta 2 and so on. For the second one, you do minus delta delta 1, but with the same tosses. I mean, so you don't toss it again. Okay, the same thing that showed up, you use the same thing here. So the gradient estimate, what he said was that we'll estimate it in this manner. So we just take the performance obtained from this simulation, which is this h of theta plus delta delta comma mu1, and take the sample performance obtained from here, which is this, take the difference and divide by 2 delta delta I to get the ith partial estimate. Now you might wonder, why is this a valid estimate? I mean, it doesn't even look like this is going to be a good estimate for this. The reason is it turns out to be a good estimate if you were to use it in a stochastic approximation scheme. And the reason is that, well, if you use Taylor's expansions of, let's say, j of theta n plus delta delta n and j of theta n minus delta delta n around theta n, both of them, and divide by 2 delta delta I n, then what you get is this kind of a thing, this kind of an expression, plus O of delta term. Now, this expression, if you expand on it, the ith term will give you grad I j of theta n, and then the remaining terms will be captured here. Okay, in this kind of a term, and O of delta is here. O of delta is of course the term that goes to 0 of its own, and also O of delta by delta goes to 0 as delta goes to 0. The important thing is that if you take the conditional expectation of j of theta and this whole thing conditioned on fn, then this turns out to be just this. Okay, because this term drops out. Simply because if you look at the expected value of delta Jn by delta In, now delta Jn and delta In, they are IID, they are independent, and they are all Bernoulli distributed plus minus 1 with probability half. And therefore, delta Jn by delta In will also be plus minus 1 with probability half, right? I mean, so if you are given this grad j of j theta n, which will be contained in this sigma algebra, so you can push it out because this is measurable with respect to the sigma algebra, and then you just have this expectation over this quantity, which is 0. So as a result of that, this term drops off. So if you were to use this algorithm in a stochastic approximation scheme, then this works beautifully. I mean, so there is no problem about it. And the interesting thing is it requires 2 simulations. So this is where our work starts in. So what we said was that we will generalize what others have done, and there have been, of course, other approaches where you can not just use Bernoulli random variables, you can bring in Gaussian perturbations, you can have Cauchy and so on, and they turn out to be somewhat better in accuracy. Particularly Cauchy is better because it is heavy-tailed and so on. So the search direction actually helps us. If you have very several minima in a narrow region and so on. If you want to get to a good minimum, I mean, Cauchy perturbations sort of help. But that's an aside. I mean, we'll not worry about Cauchy here. So what we did was we looked at this book by Asmussen and Glynn, which is this book cited here. And then I think chapter 7 or so of this book sort of looks at the scalar case where J is a map from R to R. But what we did was to extend that to the case where J is, I mean, it's no longer a scalar, but vector valued. And moreover, it's, yeah, so we had to look at the multivariate version of the Taylor's expansion. They looked at the univariate case. So we looked at this multivariate Taylor's expansion, which essentially is this. And you can, so here d beta j theta are essentially the derivatives of j of theta, which are described here. And you can sort of put them together in this manner, that summation of delta delta. So this capital delta is again the same as what I was using. I mean, the Spal's delta, right? I mean, this is a vector of, let's say, plus minus 1 valued Bernoulli random variates. And this small delta is a little perturbation. So delta delta d, this d is here. I mean, this d whole power beta by beta factorial j theta. Now, if you view this whole thing, forget about j theta because j theta doesn't depend on any of this. So suppose I look at this, I can call that as an operator acting on j theta. That's what we do. And this looks like an exponential. So this is an exponential operator. So e power delta delta d. Okay, so that's what I do. So I'll call tau delta delta j theta as j of theta plus delta delta. Again, look back. So j of theta plus delta delta is some tau delta delta of j theta, right? You push, this is like a shift operator. So tau delta delta acting on j theta is j of theta plus delta delta. So this is a shift operator. So essentially we can write tau delta delta as exponential of delta delta d. And therefore d is like 1 over delta delta of log of tau delta delta. And where the way to view this 1 by tau, 1 by delta delta, because delta is a vector of delta 1 to delta n. So what we say is that, well, suppose the way to interpret it is 1 by delta delta is this, okay, 1 by delta delta 1 all the way up to 1 by delta delta n, the vector of all of these quantities. Now we have this log. So if you use an expansion of the log function, the d turns out to be just this, okay, where I is the identity operator and this is the shift operator. Okay, so now if you are looking at the expansion of tau delta delta minus identity power j, the way to view it is, well, if I come up with terms like this, tau delta delta power k, I will view it as tau k delta delta. I push it by k delta delta instead of, yeah, so it's a k times composition of tau delta delta. So that's what this will be. So I can break this down, break d down into n operators, d1 to dn, where the ith operator will be, instead of 1 by delta delta, I'll have 1 by delta delta I of this whole summation which carries over. The thing is that, well, this will be a perfect Taylor series expansion, goes all the way up to infinite number of terms, assuming that j of theta is infinitely many times continuously differentiable. But in practice, you don't have those many times. I mean, so you may be able to have functions that are, let's say, k times continuously differentiable. So for such cases, what we said was we'll restrict this, the summation, from j equals, instead of j equals 1 to infinity, we'll restrict it to j equals 1 to k, let's say. So so we call that as an order k estimator, and that is obtained by truncating this series until k terms. So dki is then basically this, where I have, instead of infinity, I have k. Okay, so a kth order S generalized SPSA estimator, would largely require that the function j is k times continuously differentiable. I mean, you don't need more than that. So let's see some cases. So what happens for different values of k? Okay, so let's say what happens when k is 1. Okay, when k is 1, then if you notice, well, when I set k to be 1, this is what it is. So tau delta delta n minus I identity divided by this into j of theta n. So this will be j of theta n plus delta delta n minus j of theta n by this. This is also a version of SPSA that is available in our textbook. And this is also referred to as the one-sided version of SPSA because it's not perturbing both sides, it's perturbing one side of it. But if you do a Taylor's expansion, this is what you get. I mean, you get this term is what I referred to earlier. If you take the conditional expectation, you get the ith partial and the remaining terms go away. And in addition, you have an O of delta n. Yeah, when you look at the second one, when you go to the case when k is 2, you have, this was considered earlier, now you have one more term. And when you expand on this, this is the form that you get, right? I mean, you have, yeah, so this is the form you get. You get 3 measurement version, wherein you have 4j of theta n plus delta delta n minus 3j theta n minus j of theta n plus 2 delta delta n divided by 2 delta delta in, right? So this is also a form of the gradient estimator. The important thing to note is that if you look at the Taylor's expansion, there are terms that directly cancel, and it's no longer O of delta n that appears. You get O of delta n square. Okay. Now, when you increase the number of measurements, you take in one more term here. You go to the third order. You require more number of measurements, but then more cancellations happen and you get a better bias, O of delta n cube, when you have, let's say, 4 measurement test GSPSA. And if you have 5 measurement, you have O of delta n power 4. And this goes on. So the idea is that you can tell me what is the level of accuracy you want in terms of the bias in your gradient estimator. And I can give you a form of the gradient estimator to use. So that's the nice thing about this result, that you can actually design your gradient estimators looking at the accuracy that you desire. I mean, if you whatever accuracy you require in terms of in terms of the approximation that is there. So in general, a K1 plus 1 measurement algorithm, or this gradient estimator will have this form, um, where of course this term CK1L sort of appears, which has this kind of a complicated expression. I mean, it turns out that this is the form it takes, and if you so it requires, of course, this K1 order GSPS estimator requires the function f to be K1 times continuously differentiable. And this is the usual algorithm that you can use, right? I mean, you can plug in, so dk1 I of j theta n is essentially this. And so the bias essentially is the following. So what it says is that for any k1, dk1 I of f theta n is essentially of this form. So you have O of delta n power k1, right? So this is the way in which it sort of goes down. And of course, as k1 goes to infinity, this term drops off completely. So so if you look at, so if let's say we look at this function j, and this function j is, let's say, k1 times continuously differentiable with a bounded k1 plus 1th derivative. And let's say the delta INs, as I said, are IID random variables, and they are plus minus 1 valued, and they are independent of this sigma algebra. And let's say if it was some alpha 1, alpha 2 greater than 0, and for n greater than or equal to 1, if you look at the expected value of j of theta n plus L delta and delta n square given theta n, this is, let's say, upper bounded by alpha 1. And the noise is such that the expected value of the square of which means the second moment of this noise is upper bounded by alpha 2. So the bias lemma essentially says the following. So almost surely, then if you look at the expected value, the mod difference of the expected value of this quantity, the gradient estimator condition on Fn, and the gradient, the true gradient, it's upper bounded by C1 into some constant C1 positive times delta by in this manner. Yeah, one can potentially extend this to more general cases. So let's say, and all that is there in the paper. So what we said was that, well, the original SPSA did not have like these unbalanced estimators. You can make them balanced in the following form. So if you recall, we had tau delta delta n as our shift operator, which was the exponential of the delta delta and d. Now you can bring in a minus delta delta n. So tau of delta and delta n minus tau of minus delta delta n, which will be the difference of these two exponentials, but then that is 2 times sin h of delta delta and d, which essentially means that d is something like this. And if you expand on this, is the form that you get. I mean, it looks complicated, but if you can actually derive some very meaningful estimators from here. So if you look at, of course, now the estimators are balanced. So every time you require in multiples of 2. So the 2 measurement estimator will be just this. It's a balanced estimator. I mean, if you look at the tau delta delta n minus tau minus delta delta n j theta n divided by 2 times this quantity. So it will be the difference of these two divided by 2. So this is actually the standard SPSA. So you recover the standard SPSA from here as well. But of course, with the GSPSA algorithm for this kind of a bias required 3 function measurements. It didn't work with 2. So that's the interesting thing. If you use balanced estimators, use the difference of these two kind of operators, then you actually get a bias that is O of delta n square, which is what GSPSA gave with 3 function measurements, not 2. Now with 4 function measurements, you actually get bias which is O of delta n power 4. And this is the balanced estimator you get. I mean, you require one simulation with theta n plus delta n, one with theta n minus delta n, one with theta n plus 3 delta n, and another with theta n minus 3 delta n, right? So these are balanced. I mean, so balanced in the sense that you have the plus, I mean, the simulation with theta n plus delta n, and correspondingly theta n minus delta n. Likewise, you have theta n plus 3 times delta n. Likewise, theta n minus. So in that sense, it is balanced, right? I mean, it's around theta and it's sort of, you look at plus and also minus simulations, and then you sort of work with them, and then so you observe. Well, of course, I mean, this is not something that one can predict. I mean, see, constructing this of their own is too difficult. I mean, you cannot really predict how this balancing will be there, so that the higher order terms get directly cancelled and so on. But this kind of a procedure helps us do that. So in general, a 2K2 measurement balanced estimator would have this form. And then if you assume again that J is 2K2 times continuously differentiable with a bounded 2K2 plus 1 derivative, then the bias result is the following, that if you take the expectation of this quantity, the estimator conditioned on Fn minus the gradient, this is upper bounded by C3 times delta n power 2K2. And there's the sort of the bound on the variance. Uh, yeah, okay, so let's move forward. I mean, we also looked at various other estimators. Why just Bernoulli IID? So in fact, in the literature, there's a lot of work on what we refer to as smooth functional estimators. This was originally due to Katkovnik and Kulchitsky. What they said was that we'll perturb all these parameter components using Gaussians, Gaussian with mean zero, and this is the covariance matrix. And let's say V and U are equal. So here is V and here is U. So you perturb using U and then you multiply with V. Okay, so you can use U to be normal, like the Gaussian multivariate Gaussian, and V is equal to U. That is the smooth functional scheme. Then there's this random direction search stochastic algorithm by Kushner and Clark that appeared in 1978. What they said was, you look at the uniform distribution of the sphere, and then you let V to be some D times U. Or alternatively, there was this algorithm that we studied where you, instead of looking at the sphere, which is like a hard computation, you actually look at a rectangle, uniform on the rectangle, and every component is uniform on let's say minus eta interval, and the V is 3 by eta square times U. So okay, so this is the relationship between V and U here. So this is RDSA, but using a simpler computation. And this one is, of course, the Bernoulli plus minus 1 and V equals U. This was due to Spal. So one can actually generalize all of this by having this kind of a general form. And so this is something that we also came up with. You can generalize this using this kind of a gradient estimator. Now, yeah, so having said that, I mean, in a few minutes, I'll try to go over why. So there are two ways of looking at it. One is either you look at perturbations, the delta n's that are going to zero, or you let them be a constant. Requires, if you let them be a constant, there are some advantages. So one of the advantages is that if you, on the other hand, suppose you let delta n to be zero, to go to zero as n goes to infinity, you require these two conditions. You require the step size to sum to infinity of the stochastic approximation scheme, and you require the square sums of an by delta n to be finite. Okay, so an is typically, suppose an is like 1 over n. You require this to be finite. So delta n could be like 1 over n power maybe 1 by 6 or whatever that is, and then you can see that these two conditions are met. But then the problem is that it sort of constrains the choice of step sizes because you have this condition. But on the other hand, if you use a constant delta, okay, then the class of step sizes increases. I mean, you can enhance that by letting, again, sum over n to be infinity, but sum over n square is finite. I mean, there is no delta n. Delta n is a constant anyway. So this is clearly a weaker requirement than the former. So the question is, well, how do we analyze such a case? Because now you are no longer converging to the true gradient. But all you can say is that you are going to be in some epsilon ball around the gradient. Okay, so the idea is that, well, your gradient estimator is going to be in an epsilon ball around the gradient. It will go to zero as delta goes to zero, but then delta is not going to zero. I mean, delta is some constant. So our algorithm is then has this form, ignoring the noise term for now, that it is the sum epsilon n is added on to this, but it's just that norm epsilon n is less than or equal to epsilon. It's not, we are not saying that epsilon n is going to zero as n goes to infinity. So to analyze such recursions, we require a little bit of machinery. What we do is we refer to as, okay, so there's something called as a Marshall map. And so there's a set valued map. So our dynamics will become eventually set valued. So suppose you have this range, so you have this space Rn and you have function that maps Rn to subsets of Rn. Okay. So we say that such a map is Marshall if it satisfies the following three properties. The first is give me any x and it maps onto a compact and convex subset of Rn. Okay, so corresponding to x1, I have this subset, corresponding to x2, I have this subset, and so on. So for any x, hx is convex and compact. And then this property, the second one is what we refer to uh, as pointwise boundedness. So what it says is that the supremum over norm w, where w belongs to h of x, is upper bounded by some constant k into 1 plus norm x for every k, for every x. And the third property is important. What it says is that h is upper semi-continuous, which means that if you look at a sequence xn in the domain that is converging to some point x within the domain, and corresponding to to this sequence, you will get the corresponding balls h of x1, h of x2, and so on. And in these balls, you look at any sequence, you pick any y1, y2, y3 that are all sitting within this. So y1 belongs to h of x1, y2 belongs to h of x2, and so on. But these are chosen in a manner that yn converges to some y, and this y should belong to h of x. I mean, essentially, so if that property holds, then we say that h is upper semi-continuous. The important thing about Marshall maps is that if you look at a differential inclusion, which essentially is something like this, x dot t belongs to h of xt. Okay, so h is, of course, is mapping from Rd to the set of subsets of Rd. And let's say that is Marshall. So in such a case, there's this book by Aubin and Selina on differential inclusions. What they show is that such a differential inclusion has at least one solution x, bold x. And moreover, every solution that is there is going to be absolutely continuous. Now, one has to, so this, you can view inclusions as generalizations of the ODE. And because earlier, I mean, the usual stochastic approximation with a diminishing step size, with a diminishing delta and sequence will converge to an ODE, right? Which is that theta dot equals minus grad h of theta or grad f of theta, whatever it is. But now it is a differential inclusion. So we'll see what that inclusion is. But when we talk of inclusions, we have to look at look at a semi-flow, which is again a set valued map. So for n, suppose x is your starting point of this inclusion. Now correspondingly, corresponding to the set valued map, you will have multiple trajectories coming out. So for any time t going forwards, let's say we are going forwards in time, at any time, at any particular time, you look at this entire bundle that is there. Okay, you will put essentially all of them together in a set. That set is essentially phi of tx or phi xt, whatever it is. So it is basically the set of all xt such that x is in sigma. Sigma is the set of feasible solutions. And with the initial condition, all of their initial conditions is x. So sigma is, of course, the set of all absolutely continuous solutions, which will, under the assumption that H is Marshall, that it will turn out that all the feasible solutions are actually absolutely continuous. We say that M is an invariant set. If for any x, if for every x in M, there exists some trajectory x belonging to sigma that is feasible, such that the whole solution lies within this M. If you start in X, start in M, you always stay in M forever. In such a case, we say that M is an invariant set. Then, yeah, so we say that a set particular, let's say a set capital A is an attracting set. If it is both compact and there is a neighborhood of, which we call as a fundamental neighborhood of this set A, such that if you give me any epsilon, there exists some T epsilon time, beyond which, if you start your inclusions trajectories anywhere within this neighborhood U of this set A, then T epsilon instants later and beyond, you are guaranteed to be in an epsilon neighborhood of A. Okay, an epsilon A is an epsilon neighborhood of A. So if that happens, then we say that the set A is attracting. And in addition, if the set A is an invariant set, which means if you start within A, your trajectory, you stay within A, then it is also called an attractor. So let's go back to our algorithm. So the algorithm was this without the diminishing delta n sequence. It's just that norm epsilon n is upper bounded by epsilon. So alternative view is you look at, let's say, g of x is the sum of gradient j of x plus this ball closed. Carry this ball along. So you have, so you look at the algorithm in this manner that xn plus 1 is xn and then minus an, and then you can be anywhere within this ball of radius epsilon around the gradient, around the true gradient. Okay, so you can have it, you can be anywhere within. Okay, so of course every time you get to a point, but then that point, all you know is you are in an epsilon ball around it. You don't know anything more than that, let's say. Okay, how far are you from the gradient? I mean, there's a bound on that, which is epsilon. I mean, that's all you know. So we'll make the following assumptions. We'll assume that grad J is continuous. In fact, sort of Lipschitz continuous. It is continuous, and in addition, you have this property, which is like a linear growth condition, which is, of course, assured if grad J is Lipschitz in particular. And the ANs are positive. The sum of ANs is infinity. Sum squares is finite. And in addition, these are like stability requirements. You suppose you have this, we define GC of X as a scaled version of this quantity. So suppose Y belongs to G of Cx. So these are like G of X is of course the ball of radius epsilon around the gradient. You scale it up by some C. So you push it as essentially, and then you look at all these points, you divide by C. All right. I mean, we call that as GC of X. And G infinity of X is the closed convex hull of the lim sup as C goes to infinity of GC of X, where lim sup is essentially containing all of these points. Okay, so set of all Y such that lim inf as C goes to infinity of the distance of Y from GC of X is 0. So what we were able to show was that that the map X to G infinity of X is Marshall. And if you look at x dot t belongs to minus g infinity of xt, this will therefore have at least one solution and which is absolutely continuous. And then let's assume that this differential inclusion x dot t belongs to minus g infinity of xt. This has an attractor set capital A, which is a subset of a ball of radius A around the origin for some A that is greater than 0. And if you close this ball, that will end up being a fundamental neighborhood of A. This is a kind of a technical requirement that suppose Cn is an increasing sequence of integers such that Cn increases to infinity as n goes to infinity. And let's assume that xn is a sequence that goes to x, yn is a sequence that goes to y, and this is such that yn belongs to gcn of xn, and y will belong to g infinity of x. So the basic stability result that we have is the following. So what we do is usually in stochastic approximation, the way to analyze is we sort of look at the continuously interpolated trajectories of the algorithm. So in this particular case, we define a sequence of time points Tn as T0 is 0, and then Tn is like summation m equals 0 to n minus 1 of am. Am again are the step sizes. So the main result says that under these assumptions that we had, A1 to A4, the iterates are stable, which essentially means that the supremum over n of norm xn is finite almost surely. Now, if we let capital M be the minimum set of J, and that let's say that is the global attractor of this this is an ODE, of course, without the because this is a true gradient, right? So the minimum set of J is the global attractor of this ODE. Then one can show that if you have any compact set K such that M is a subset of K, and that will end up being a fundamental neighborhood of M. And so it follows then from this result, because we have proved stability. And if once we show stability, then X bar T will belong to K0 for some compact set, which can be sample path dependent, which then ends up being a fundamental neighborhood. See, if you have stability, then of course all your iterates are bounded and they are within you can close this set, then it will be within the compact set. But of course, that compact set is by itself sample path dependent, which is fine, right? I mean, as long as you are within a compact set, you can use that as your fundamental neighborhood on that particular sample path, and then you argue that, well, this is the fundamental neighborhood of the set M. And so the result that we have on asymptotic convergence is that given a delta, there exists an epsilon such that the recursion that we have converges actually to a delta neighborhood of M, the minimum set, provided that epsilon is below this epsilon of delta by 2. And the way to work that out is, as I said, you look at these, this time is sort of split into these intervals T1, T2, and so on, where T1 is like T0 is 0, so T1 minus T0 is A1, T2 minus T1 is A2, and so on. And we know that sum over n is an is infinity, so this time line goes all the way to infinity. And at time 0, you plug in your recursion, whatever value this was taking x0. Then at time t1, it was x1, time t2, it is x2, and so on. And then you linearly interpolate all of these. So you get a continuous trajectory. This is your algorithm's trajectory that we call as x hat, x bar of t. And then you look at the corresponding trajectories of the differential inclusion. Of course, right now I have plotted only one of them. But in general, you will have a semi-flow coming in. So you look at, let's say, for simplicity, for the ease of visualization, this is the trajectory of the corresponding the one trajectory of the corresponding differential inclusion. But what you do is typically every capital T instance. So for some capital T, you sort of reset the ODE or the inclusion to start off from the same initial condition where the algorithm is at that time. So T1, you reset your inclusions trajectory to start off from here. And again at T2, you do the resetting and so on. Now, one can show that as time increases, the norm difference between the ODE, the inclusions trajectories and what we obtain from the algorithm will collapse. Essentially, they will come in the limit as n goes to infinity, the supremum norm difference between these two will go to 0. And now we know that, well, the differential inclusion is going to an attractor, and therefore the algorithm will also converge to that same attractor. I mean, roughly that is what it is. We also did a finite and as a non-asymptotic analysis, and this is the bound we get. I mean, I'm running out of time, so I'll probably move very quickly. So the kind of bound we get on the mean squared error is essentially if you compare the GSPSA estimators bound with the unbiased gradient estimators bound, what we observe is in the end, if K is large, then of course this becomes something like 1 over square root n. And an unbiased gradient estimator is also square root of 1 over square root of n. And then the usual SPSA bound is like this, O of 1 by m power 1 by 3. Okay, so which means that you can actually do much better than SPSA, right? I mean, using just these zeroth order estimators. Yeah, the student essentially did a lot of simulations. So this is the Rastegian function, which has several local minima and so on. There's one global minimum at 0, 0, 0. And then there is this quadratic function. Quadratic is, of course, a convex function, assuming A is positive, definite, and so on. And then the performance was measured in terms of the parameter error. And here are some plots. See, what is observed is that if you increase the number of simulations, which means you go up in the order, then the parameter error kind of diminishes. I mean, you can actually make it very less by increasing the order suitably. And here are some numbers, essentially just to sort of reinforce that whatever I said. So as you increase K, you sort of will see that this the performance for various values of dd is the parameter dimension, that improves. So in the quadratic case, of course, it's a convex objective. So even small k values also work well. I mean, in this particular case, it turns out that this is the best as opposed to the others. But when you have more number of local minima, then essentially the as you increase k, you get a better performance. Yeah, these are some more experiments with with other estimators, the random direction, stochastic approximation, the smooth functional, the gradient, the generalized versions of these. And again, it's seen that if you increase k, then you get better performance. Again, GRDSA with the quadratic and GSF with quadratic. This was Astigen. And if you use balanced estimators, then you get again you get better performance than with unbalanced estimators. With unbalanced and d equals 5 is the kind of plots you get. We're assuming k2 is 1. And with k2 is so with k2 is 1 in the unbalanced case and k2 is 2, the number of the computational effort is the same. Because here also you require 2 simulations, here also you require 2 because it's k2 plus 1 that comes in. So when D is 5, you see this kind of a performance, but then the red line which corresponds to the balanced one shows much better results. So balanced estimators are better in general. Yeah, so these are some more results. And yeah, so in general, there is a summary table which says that if you use finite difference stochastic approximation, you do require 2D function measurements. But then the bias is O of delta n square. With SPSA, which was a SPAL, you do need 2 simulations. Bias is this. RDSA, again, these are from the literature. 2 simulations, you get this. But these are our algorithms. So if you use more simulations, you get a bias that, I mean, of course, with the less number of simulations, you match exactly what these are giving. But in general, if you are able to have, if you are sure that your function is, let's say, k times continuously differentiable for some k greater than 2, then you can do better than what SPSA and RDSA would. On the other hand, if SPSA and RDSA would continue to give this kind of an accuracy, even if your function were k times continuously differentiable. So you can, so that's the sort of trade-off between these algorithms as opposed to us. Some more work that we are continuing to do, largely in terms of Hessian estimation, and then looking at some applications in reinforcement learning and some natural language processing, which is kind of the in thing these days. And then looking at some asymptotic normality results. These are like in the sense of central limit theorem. So can we talk about the rate of convergence? The non-asymptotic bounds that I talked about was not in the asymptotic regime, but if we are talking of the rate of convergence in the asymptotic regime, then essentially what would you get? I mean, so this is currently ongoing. Okay, with that I'll stop and we'll be happy to take any questions.
Question? With this multiple differencing kind of algorithm, so is there also some numerical stability issue that comes up, at least in the non-noisy setting? Because so it's sort of like, for example, if you're canceling too many, like if there are too many large values, then the actual value, the difference that you're trying to compute is very small. Then it's these like because you are doing this floating point arithmetic, like taking larger and larger number of differences. So is that trade-off there anywhere, or it doesn't appear in?
I see. Yeah, you are saying numerical stability issues when you use large values of k, is it? Is that the...
Yeah, essentially because you're taking differences. I mean that can happen even at k equal to 1, I guess. But because so the issue can arise if the so okay. So in the end, so you have some number of values, and
Right.
a combination of them, but the final answer can actually be much more than any one of the linear.
All right. Yeah, no, the good thing about these estimators is that you get a direct cancellation. So the numerical stability does not arise. I mean, because the issue of things going bad does not arise because if you do a Taylor's expansion, you get a direct cancellation of the higher order terms. I mean, kth up to kth order terms, they all cancel off directly. I mean, they just don't appear. So that is so as a result of that, we didn't observe a numerical stability issue as such. Uh, but I guess if you have,
This
I mean,
will become larger and larger as you increase the order. Is that
right. Yeah, as you increase the order, you do get better performance. I mean, because and that sort of also showing up in this kind of thing. Does that answer your question? I mean, I'm not sure. Sorry.
Yeah, so I think maybe so the thing I was concerned about is that because another thing that is happening is that I think as k increases the coefficient that appear that you have to multiply the evaluations by, they also increase in magnitude.
Okay. Oh, you mean to say that the
So at some point, like this kind of floating point issue might come, but I think in these examples probably it doesn't. I think that will probably happen at very large scale, which are not practical or something.
you mean that if you look at
Yeah.
something like this, is it? I mean,
So for example, in the previous one, there was I think we have a few slides before there are apps, their actual values. Yeah, like this, for example.
okay. No, but again, if you yeah, so basically I haven't written the Taylor's expansion here. But if you do the Taylor's expansion of this around theta n and this around theta n, then the k up to k, these terms will go away. So that's the important thing. I mean, of course, this minus this whole power 2j plus 1 is there. But the expansions are such that if you work this out, then until the k2th order, you don't get any terms. So that's so as a result, you don't really see anything blowing up as such.
Any other questions? Yeah, that's fine.
Okay, thank you. Thank you very much.